At Electronica this year, Maxim Integrated is showcasing system-level solutions that really leverage our highly integrated products. So one of the demos I want to show you is our factory automation demo, and it's shown right here. And what you see there is a robotic arm and a conveyor belt, and we call it our beer mug factory that we built the PLC for, and we call it a micro PLC. So in that micro PLC, we're able to shrink the size down to less than half of what you would find in a normal PLC. It runs 50% cooler, so dissipates half the amount of heat, and allows us to put it in a small space, and it runs at just a few microseconds, so maybe 70 times faster than a traditional PLC. Products that allow that to happen are high efficiency power supply products, where we get rid of the Schottky diode and we do the rectification with a synchronous rectifier. That cuts the power dissipation in half. We also have digital output parts for some of the control here. They run at high speeds, like they can circle at 100 kilohertz kind of rates, and they have about 85 milliohms of resistance. So you can drive like multiple amps through them. That's pretty cool too. So what we decided to do is make a complete functioning micro PLC. And this has digital I/O cards, analog I/O cards, a power supply card, a communications card. And each of these cards showcases 5 to 6 or 7 different Maxim products. And then what we do is we provide these cards as reference designs to customers so they can get a head start on designing like the system using Maxim parts. And it gives them like the ability to save time to market, calendar time, as well as R&D dollars. These reference designs have, of course, the schematics. They have all the parts in there. They have the Gerber files, and they come with a nice out-of-the-box experience. So what I'm showcasing here is our ultrasonic flow meter demo, and it features this ultrasonic flow meter that we offer as a complete working flow meter reference design, and it features our Max 35101 IC, which is essentially an analog front end. And the way this works is it looks at the rate of water flowing through some sort of system, and what's really great about it is it can detect very low flow rates. Here, let me show you what I mean by that. So what this demo is illustrating here is going to be the difference between the accuracy level of a traditional mechanical rotating wheel flow meter, and this shows the flow and the number of liters that are going through that, and our ultrasonic flow meter, which uses piezoelectric sensors to measure the time of flight of the ultrasonic signal, and it does it with 20 picoseconds accuracy. Here, let's start with the high flow rate, and so the water's flowing through there at a pretty high rate. The mechanical wheel and the ultrason's working fine. We turn it off. So you see, when I get a nice low flow rate going here, we continue to see water flowing through the ultrason meter, but on the mechanical wheel, you don't see any change. There's not enough water flowing through there to cause it to spin. And most leaks that take place in the world take place at these very low rates, so it's important to be able to detect them in all kinds of applications, whether it's utility meters or more commercial applications like detecting leaks in pool filtering systems or in industrial pipes and other applications like that. So what you see in this system is a patch that you apply to your body, and it's comprised of 2 chips. One of them is a clinical grade temperature sensor. It's accurate to a 1/10 of a degree. And the other chip on there is a secure near field communication chip. And you put them on your body, and the idea is you could go ahead and read a temperature on a patient without actually having to contact the patient, which of course reduces the amount of cross-contamination in hospitals. So pretty neat product there. What's interesting about this is it uses energy harvesting, so there's no battery in the system. It harvests the energy that comes off the NFC request and other wavelengths that might be in the air, and then when you go to do your reading, it provides enough energy to do the temperature test and transmit back to you using just energy harvesting. And then when you're done, you throw it away.